5. The relation between validity and implication. Let us begin this section by recalling some earlier definitions. In section 1, we noted that a formula A is a tautology if and only if it is true in every case. We can describe this by saying that a tautology is a formula that is true no matter what. By contrast, a contradiction is a formula that is false in every case, or false no matter what. Between these two extremes contingent formulas, which are true under some circumstances but false under others. Next, in section 2, we noted that a formula A logically implies or simply implies a formula B if and only if the conditional formula AB is a tautology. The notion of implication is intimately associated with the notion of validity. This may be illustrated first using the simplest example, an argument with just one premise. Consider the following argument form. A 1p/p and q. You might read this as saying that it is not true that p, so it is not true that p and q. On the other hand, consider the conditional formed by taking the premise as the antecedent, and the conclusion as the consequent. See 1p, p and q. As far as the symbols are concerned, all we have done is to replace the /by. The resulting conditional may be read as saying that if it is not true that p, then it is not true that p and q. There seems to be a natural relation between a 1 and C1, though it is clearly not the relation of identity. Whereas a 1 is a pair of formulas, C1 is a single formula. Nevertheless, they are intimately related, as can be seen by constructing the respective truth tables. PQP/P and QPP and Q1 TTF 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 TTT2 TFF TTTFF TTTFF 3 FTTF TFF TTF TTFF T4 FFTF TFF TTF. We now have two truth tables side by side, one for the argument P/P and Q, the other for the conditional P and Q. Let's look at the conditional first. The third column is the final output column, and it has all T's. So we conclude that this formula is a tautology. In other words, no matter what, if it is not true that p, then it is not true that p and q. This is reflected in the corresponding argument to the left. In looking for a case that serves as a counterexample, we notice that every case in which the premise is true, so is the conclusion. Thus, the argument is valid. This can be stated as a general principle. Argument PC is valid if and only if the conditional formula PC is a tautology. Since, by definition, a formula P implies a formula C if and only if the conditional PC is a tautology, this principle can be restated as follows. Argument PC is valid if and only if the premise P logically implies the conclusion C. In order to demonstrate the truth of this principle, we can argue as follows. Suppose that the argument PC is not valid. Then there is a case, call it case N, in which P is true but C is false. Consequently, in the corresponding truth table for the conditional PC, there is a case, namely, case N, in which P is true and C is false. Accordingly, in case N, the truth value of PC is TF, that is F. It follows that PC is not a tautology, so P does not imply C. This demonstrates that if PC is not valid, then PC is not a tautology. We also have to show the converse conditional. If PC is not a tautology, then PC is not valid. Well, suppose that PC isn't a tautology. Then there is a case in which PC is false. But a conditional is false if and only if its antecedent is true and its consequent is false. So there is a case in which P is true but C is false. It immediately follows that PC is not valid. This completes our argument. Note what we have in fact demonstrated is this: the argument PC is not valid if and only if the conditional PC is not a tautology. The statement has the form VT. The student should convince him herself that VT is equivalent to VT, which is to say that VT is a tautology. The above principle about validity and implication is not particularly useful because not many arguments have just one premise. It would be nice if there were a comparable principle that applied to arguments with 2 premises, arguments with 3 premises, in general to all arguments. There is such a principle. What we have to do is to form a single formula out of an argument irrespective of how many premises it has. The particular formula we use begins with the premises, next forms a conjunction out of all these, next takes this conjunction and makes a conditional with it as the antecedent and the conclusion as the consequent. The following examples illustrate this technique. Argument associated conditional 1 P1. P2 per caret P1 and P2 C2 P1. P2. P3 per caret P1 and P2 and P3 C3 P1. P2. P3. P4 per caret P1 and P2 and P3 and P4 C. In each case, we take the argument, first conjoin the premises, and then form the conditional with this conjunction as its antecedent and with the conclusion as its consequent. Notice that the above formulas are not strictly speaking formulas, since the parentheses are missing in connection with the ampersands. The removal of the extraneous parentheses is comparable to writing x plus y plus e plus w in place of the strictly correct x plus y plus e plus e. Having described how to construct a conditional formula on the basis of an argument, we can now state the principle that relates these two notions. An argument A is valid if and only if the associated conditional is a tautology. In virtue of the relation between implication and tautologies, this principle can be restated as follows. Argument P1. P2. PNC is valid if and only if the conjunction P1 and P2 end, and Pn logically implies the conclusion C. The interested reader should try to convince him herself that this principle is true, at least in the case of two premises. The argument proceeds like the earlier one, except that one has to take into account the truth table for conjunction in particular. P and Q can be true only if both P and Q are true.